All right, welcome to this explainer. Today, we're going to tackle a highly praised breakdown of the Open Systems Interconnect model, or as you probably know it, the OSI model. We are finally going to make networking just click for you. You know, if you've ever found yourself wondering how the internet actually works, literally layer by layer, from the actual physical cables plugged into the wall all the way up to the screen you're staring at right now, well, you are in exactly the right place.
And look, I get it. Many people struggle with these abstract networking concepts for literally years. It can just feel like this massive jumbled alphabet soup of acronyms. But check out what one reader of our source material actually said. 8 years, excluding college, this is the first time I understood the OSI model. Thank you so much. See, looking at this stuff for the right lens, it changes absolutely everything.
So, to kick things off, we really have to ask the fundamental question of all network engineering. How on earth does a packet get from here to there? Seriously, how exactly does a tiny digital message travel from your smartphone to a random server halfway across the globe in a fraction of a second, without just getting completely lost?
Well, here's our agenda for how we'll figure that out. First, the internet's moving parts. Second, layer 1, physical connections. Third, layers 2 and 3. Then, layer 4, transport. Followed by layers 5, 6, and 7, and finally, encapsulation and decapsulation. We're basically going to build this model from the ground up.
All right, moving into section 1, the internet's moving parts. This is the cooperative engine of the web.
Okay, let's dive right in. The OSI model is essentially a set of 7 independent functions, which combine to accomplish the ultimate end goal of computer-to-computer communication. Basically, it just explains all the individual isolated jobs that are completely necessary for the internet to, well, work.
Actually, it's a lot like a car. Think about it. You've got a battery, an engine, and an axle, right? These are totally independent parts that a mechanic could work on completely separately, but they have to combine to create forward motion. If your battery is dead, the axle's condition doesn't really matter, you're not going anywhere. The OSI model works exactly the same way. As long as each independent layer is doing its job properly, the data moves forward.
Which brings us to Section 2, Layer 1, Physical Connections. Welcome to the realm of ones and zeros.
So, this is absolutely crucial. Layer 1 is the physical layer. We're talking about anything that carries the raw ones and zeros between two nodes. This could literally be electric pulses running through an Ethernet cable, it could be radio waves flying invisibly through the air for your Wi-Fi, or it could even be pulses of light shooting down a fiber optic cable. The hardware here includes the actual cables, repeaters that boost the signal, and hubs. Basically, the rule of thumb is, if it moves a raw bit from point A to point B, it lives at layer 1.
Let's level up. Section 3, layers 2 and 3. This is all about navigating the network.
Okay, so layer 2, often called the data link layer, interfaces directly with that physical wire we just talked about. It takes those raw, chaotic ones and zeros and groups them into nice, organized little chunks called frames. Now, to figure out where these frames actually need to go on the local network, layer 2 uses MAC addresses. These are physical addresses that are permanently burned into your network interface card, your NIC, by the manufacturer. Oh, and the primary devices operating at this layer? Those would be your network switches.
But wait, this brings up a massive question, doesn't it? If we already have a unique Layer 2 MAC address permanently burned into every single network card in the world, why on earth do we need Layer 3 IP addresses at all? It's a super common point of confusion for anyone getting into this stuff.
Well, the answer is simply that they accomplish entirely different jobs. Layer 2 uses MAC addresses, which, like we said, are permanent and physical. It's kind of like your social security number. It belongs to the hardware itself and it never changes. But Layer 3 uses IP addresses, which are logical and definitely not burned into the hardware. Think of the IP address more like your mailing address. If you take your laptop to a local coffee shop, joining a completely new network, your IP address changes to fit that new location, even though your physical MAC address stays exactly the same. So routers operate at this Layer 3 to bridge the boundaries between all these different networks. So the really critical takeaway here is the delivery scope. Layer 2 is strictly responsible for packet delivery from hop to hop, meaning it just gets the data to the very next device on the path, like from your computer to your home router. Layer 3, however, is the big picture. It's responsible for packet delivery from end to end, meaning from the original source computer all the way across the globe to the final destination server.
All right, making our way up, Section 4, Layer 4, Transport, distinguishing the streams.
imagine your computer right now for a second. You probably have a web browser open, maybe you're streaming some background music, and you've got a chat app running. All that data coming from all those different servers is arriving as one massive blended jumble of ones and zeros right on your single network card. So, Layer 4, the transport layer, steps in to distinguish these network streams. It separates the data out so your streaming music doesn't accidentally show up as weird text code in your web browser.
And how does it do that? Well, to manage all these applications, Layer 4 relies on a pretty massive number, 65,536. It assigns unique port numbers across the TCP and UDP protocols. So when a packet arrives, Layer 4 looks at the port number and says, okay, this belongs to port 80, send it to the web browser. Or hey, this one belongs to the chat app. It's brilliant. That is exactly how your computer perfectly sorts the incoming traffic.
Let's take a quick breather and summarize everything we've built so far. Layer 2, the data link layer, uses MAC addresses for hop-to-hop delivery. Layer 3, the network layer, uses IP addresses for end-to-end delivery. And Layer 4, the transport layer, uses port numbers for service-to-service delivery. Honestly, it's just a perfectly elegant system of passing the baton.
Almost at the top, Section 5, Layers 5, 6, and 7, displaying to the user.
These are the session, presentation, and application layers. Now, from a purely network engineering perspective, these top layers handle the final steps before data is actually displayed to you, the user. They deal with all the formatting, the encryption, and specific application commands. In the hardcore networking world, because the primary job of actually delivering the data is already done, folks often just group these together simply as L5 through 7.
And finally, Section 6, Encapsulation and Decapsulation, the grand reveal. Because this is where the real magic of the OSI model happens, encapsulation and decapsulation. This defines exactly how data is moved through the layers from top to bottom when you're sending a message, and then from bottom to top when you're receiving one. It's literally like putting a letter inside an envelope, putting that envelope inside a box, and then tossing that box into a massive shipping crate.
Let's walk through the encapsulation process when you send data. As your data moves down the stack, each layer adds what's called a header, which is just the specific info it needs to do its job. First, Layer 4 slaps on a TCP header containing the source and destination ports. Then it hands it down to Layer 3, which encapsulates all of that inside an IP header containing the IP addresses. Finally, Layer 2 wraps the whole shebang inside an Ethernet header containing the MAC addresses. Only after all of that is it converted into physical ones and zeros and blasted out over the wire at Layer 1.
Now, on the receiving end, the exact opposite happens. As the ones and zeros flood in, the system decapsulates. Layer 2 reads and strips off its Ethernet header. It then passes the package up to Layer 3, which reads and strips off the IP header. Then Layer 4 strips off its port header. Every single layer removes its specific piece of the puzzle, passing the remaining data up the stack step by step until just the pure, unadulterated data reaches the final application.
So keep in mind, the OSI model is really a conceptual tool, a master framework, rather than some strict, unbreakable rule. But honestly, having this mental map, it changes everything. So here's the crucial takeaway for you. Now that you understand how these 7 independent parts form the true engine of the internet, how are you going to use this framework to decode, understand, and troubleshoot your own networks? Keep that in the back of your mind the next time you plug in a cable. Thanks for joining me on this explainer, and keep learning.